Postgres 18 has been released with many anticipated features, including UUID v7 allows you to get these beautiful ordered UUIDs. PG over explain gives you more details in your execution plan when you run explain. And the most important feature of all is Asynchronous IO, which is the topic of this episode of the Backend Engineering Show. You see, Asynchronous IO is a necessary evil. It gets you the performance that you need, but at the cost of complexity. The Postgres team has been working on this feature to enable Asynchronous IO for over 5 years, since 2001. It's a complex implementation, it's a complex project. So unless you start from scratch, which Postgres didn't, there's a lot of baggage. There's a lot of clients using it, so we shouldn't be breaking stuff. So in this episode of the Backend Engineering Show, I want to explain what is Asynchronous IO and how does the Postgres in version 18 implements Asynchronous IO. How about we jump into it? Welcome to the Backend Engineering Show with your host Hussein Nasser, and we need to start with the idea of synchronicity versus asynchronicity. I talked about this many times in this channel and my podcast. Essentially, to be synchronous is, think of it as a client. You're calling some sort of an API, some sort of a backend, some sort of a server. Doesn't matter. If your call blocks the execution of the rest of the instructions in your program, that is a synchronous call. We call this API synchronous because it did not allow you to move to the next instruction unless you get an answer. Okay, so you're blocked, and when you're blocked, you don't get to execute the rest of your instructions. Asynchronous, on the other hand, is you run and you delegate that job to some other party often, and then you move on. And then sometime later, you either check if this is ready or you get a callback, like with NodeJS, how NodeJS does it. That, hey, your result, remember this thing that you asked about a few milliseconds ago? It's ready. You can get the results here. So that's the gist of synchronous versus asynchronous execution. Okay, and we can dive into details just by that, but we want to kind of move that into the IO concept. So what does it mean to do asynchronous IO? We're kind of giving some concrete examples here. We're doing an IO. That means it's either a read or a write. In this context, since we're talking about Postgres, we're not talking about network, which is its own beast. We're talking about files, right? We're reading and writing to disk, right? And we're dealing with system calls, that is the kernel system calls, that allows us to read from files, because database is just a bunch of files, believe it or not. Yeah. Shocking, right? The kernel provides you with a beautiful system calls that allows you to do IO. Often, all of these methods are synchronous. That means read, for example, is a system call that allows you, given a file descriptor that you have opened for a file on disk, I want to read that file, and I want to put whatever I read, this many bytes, in this pointer, copy the data, and move it to this memory location where it lives in my user space. That's a read call, and that is a blocking call. It's a blocking call. If you call that, your process will switch from user mode to kernel mode because you called a system call, and then that's it. You cannot move to the next instruction. You cannot. Your process is blocked because it's synchronous, right? And until the kernel take that read, talks to the IO controller, NVMe or whatnot, does the actual block read, gets the result. We're talking here about buffered IO, so we're writing into the page cache, to the kernel page cache, and then gets that, get a copy of that whatever we read into the page cache, and then we get you now from the page cache to your memory location, and that is a CPU cost. You're copying data from the page cache into your specified buffer. Okay, so that's a read. Write is identical, right? It just works the other way, right? But it's synchronous, right? So I'm blocked when I do that. What's wrong with that? Well, if it's wrong, if you're doing a read, you get something and you read it. Think of it, implement a full table scan. You read, get something, process it. Read, block, get something, process it. As opposed to read, execute, and then let me worry about that later. Okay. So yeah, think about it. Why is it slow? Well, it's blocking. It's not allowing me to do other things that I might need to do as a process. Like I can be doing tons of CPU intensive work and you just blocked me? How dare you? That is rude, right? So synchronous IO, that's it, blocking. Asynchronous IO allows you to unblock yourself. Well, the oldest trick of the book to do asynchronous IO is to offload it to a thread or another process. So we're still doing synchronous IO, but someone else is blocked, not me. I'm free. I'm free. As a main process, I'm free. I'm just gonna spin a process and I'm gonna ask that process to actually do the IO for me. Guess who's doing that? NodeJS. Yeah, for the longest time, NodeJS exclusively worked on that mode. For files. Don't yell at me, for files. Network is a different beast. I talk about all of this, by the way, in my NodeJS course. If you're interested to know the details and the inner workings of this, go head to node.win, W-I-N. It will redirect you, get you a coupon. Worker thread. Beautiful design. Nothing wrong with that. Right? So let do the asynchronous IO, but let someone else get blocked. So we're still getting blocked, right? And Node.js, by the way, uses a library called libuv to implement that piece. Right? In recent releases, they switched to IOing, which is what we're about to talk to next. Right? But essentially, the worker pool is a very nice idea to do asynchronous IO. It's just like let someone else be blocked. It's a very simple design, yet we still give the feel of asynchronicity. Okay, so that's asynchronous IO. Now, asynchronous IO, again, I'm talking about file IO here, nothing about network, different beast again. Here, asynchronous IO, there is a new interface. I say new, it's been there for years now. It's called IOUring, which is a shared memory between the kernel and the user space, where the user can submit a job and the kernel can pick that job, actually does the read, and then writes back the results into the into the shared memory space, and then the user can check if the result is ready. So it's a pure asynchronous model. If you really think about it, someone else is doing the blocking read, and that's the kernel, right? We're just offloaded the game. That's the whole game, by the way. We just tell someone else to do it. It's just we present it in a pretty way. Okay, so everything at the end of the day is synchronous. There's no escape. Someone else has to pay the price, right? Okay, So that's IO Urang. Of course, I think Node.js supports it. Right? I keep referencing Node.js because Node and all these framework and Postgres, they're all software. They all need to read from disk and do network, and they're all kind of a backend infrastructure, which is the specialty of this channel. So Synchronous IO, Asynchronous IO briefly. So let's talk about Postgres prior to 18. Okay, prior to Postgres version 18, each time you as a client connect to Postgres, a new process is spun up dedicated for that session, for that connection that you created. In Postgres speech, they call it a backend. So if you hear the word backend from a Postgres maintainer, they don't mean the actual backend as a Postgres or your application. No, they mean that process that got spun up when you connect to your Postgres instance, right? So your backend application can connect to Postgres, and that's spin it up in a backend process, because they just call it backend. So that backend process actually does your execution for your queries that you send. So if you send a SQL query, that backend process receives it, parses it, produces an execution plan, probably reuses one if one already exists. Hopefully used some bind variables so you don't recompile your statement every time. But then eventually we're gonna need to do some IO. In Postgres 17, prior to 18, right, the backend process does just synchronous IO. That means it needs to read the table. Let's think of a simple example like a full table scan, right? Sequential scan. I'm just reading, doing a count, right? Perfect sequential scan example. So I have to scan the entire table to count. So I'm reading the first page, right? And then that page, I issue a read, and I'm blocked until the kernel tells me, yo, there you go. Here's your page. And then the backend stops processing this page. Then it sends another read. Page 2, page 3, page 4, page 5, page 6, page 7, page 8. But you get it. So it's a synchronously blocking call. Right? Of course, we cannot parallelize anything here. Well, you need to be careful. There is parallelizing in the Postgres using another method, another sets of processes using parallelism. But let's assume this is disabled, right? It's a complex system, so I need to watch what I'm saying, right? So let's assume there are no parallelism, but yeah, in this case, it's going to be serial. And you're suffering. Postgres 17 is better than 16 in that regard because it tries to combine IO based on certain heuristics that, well, I'm doing sequential scan. Why am I reading 8K pages at a time? Well, why am I reading one page at a time? 8 kilobyte is the page size in Postgres, right? Why am I doing that? Let's combine them. Let's read 288 kilobyte. I don't know why I picked 288. But yeah, just issue one read as opposed to 5 or 10. Why do I need to do that? Like, why? Yeah, let's do 80. Let's do 10 pages at a time. The problem with that is, like, if you might read more than you need, you might pull in more data than you need. And as a result, you're going to use more memory than you need in shared buffers. And you're going to need the most precious resources, CPU. You're going to use more CPU than you ever need. And boy, CPU is expensive with these IOs. Because, yeah, I am doing a read, but the CPU is the bottleneck here. Because we're copying from the page cache, from the kernel page cache, down to our, up in this case, to our user space applications. So there is a lot of the CPU is busy It's just like copying to the registers and then flushing back to the memory and copying to the registers and flushing to the. If you see what's happening, you're gonna be disgusted at the number of IOs that you're gonna use. Like, and you're gonna feel for the CPUs. Like, what have I been doing for these poor CPUs? And then you're gonna really feel bad, and you might not go to sleep. You might not even go to sleep because it's like you'll be feeling so bad about all the nasty code you have been writing. Sometimes we don't have a choice, but there is a choice around this buffered IOs, right? Which is called direct IO. So you skip the page cache, go directly to disk. But that's a different beast. We're gonna talk about it in a bit. But so that's what Postgres 17 does. It combines them. 16 didn't. It used to do this one by one. And of course, 17 got smarter about read aheads with the kernel. That's another thing, configuration in the kernel. That if you issue a read, it kind of anticipates that, well, I'm not going to just read what you ask me. I'm going to read more. I'm not going to give it to you. I'm not going to give you more than you asked. Yeah, you asked for 8 kilobyte. I'm going to give you 8 kilobyte. But I'm going to pull 100 kilobyte just in case you're going to need it, right? Just the read ahead of this. And you can configure this in Linux, the kernel. I think in Windows too. I'm not sure. So we talked about Postgres 16, Postgres 17, and the cost of the backend being synchronous, right? So that's this. We're still blocking here, right? I'm issuing a read, I'm blocking until this is received, and then I process it, right? So I cannot do any CPU operations, use the CPU effectively when I'm waiting blocked by this process. And what makes this worse is the kernel might switch you out as a process from the CPU because you're blocked. Hey, what are you doing here in the CPU? You're not doing anything. You're just blocked. And if it sees you doing nothing, you're gonna get kicked out and get that other process that is hungry for CPU better than your lazy ass sitting there not doing anything. Yeah. So Postgres 18 came in with a fantastic idea, which is asynchronous IO, which took years to implement. Like I'm gonna reference the video the 2025 talk, the latest talk by Andreas. I think I pronounced his name right. Andreas is he works for Microsoft, but Microsoft just pays him to work for Postgres, which is kind of amazing if you think about it. You work for a company, and that company's like, yeah, you can do your open source stuff, sure. Right? That kind of just like it builds a reputation for Microsoft, which is I found that amazing, right? So he's been working for 5 years on this asynchronous IO, because you gotta think about this, guys. Postgres has been there for more than 30 years as a project. It's an old code base. If you ever worked with an enterprise company, which I do, you're gonna see code bases that are legacy code bases. And these are not like, oh, let's just rewrite it in Rust kind of a situation, right? You need to maintain this, and because there's just so many features that is almost impossible to build all of them. Again, there's tons of layers and layers and layers and layers of features that are all dependent on each other, and tooling building on top of it. It's impossible to rewrite, right? It's a very hard thing to rewrite. You can, but it's a very hard thing. So Postgres is one example of this, where you cannot just create a new thing and just build it. You have to kind of work yourself in to understand how the code works, even the legacy pieces, and make sure that it actually works. So there is a lot of people that invested in architecting Postgres from the interface layer, how reads are performed, to make it abstraction, to introduce new abstractions. It's called the stream reads, if I'm not mistaken. And I'm not familiar with the details, to be honest, but that's how I understood it. So there's like create an API to remove this concreteness from the consumers as Postgres code. So it introduced this streaming layer as a read API, and then that got plugged in the new code. The guts has changed. Now, after all that, making sure all the tests has succeeded, then the guts started to change to start to support asynchronous IO. So the first method that got supported is to be able to do workers, which is a connection pool, a worker pool. My mode is always connections with networking and stuff. So a worker pool. Yeah? So spin up 3. That's the default, I think. It's very low if you ask me. 3, just 3. That's all right. So you have 3 workers, and those 3 workers are shared between all the backends. So if you're going to execute an IO, then you issue the IO to one of these workers, and they will do the synchronous IO. They will be blocked, not you. You're above them. You're the king as the backend process, right? You get to do other things. So you can do issue 3, 5 reads. Yeah, some of them will get queued, but then you can do, as you start receiving. Now, that's a question. How do you then receive the results? You can see how rewriting the code becomes very complex. Yeah, if you're used to NodeJS and promises, you must say, how hard can that be? Well, NodeJS written from scratch to be asynchronous IO from the first beginning. It was written to be this way. So you have nice callbacks and promises, and async awaits. Postgres have none of that stuff. So all of this code was written synchronous, right? So you have to rewrite it to take advantage of being asynchronous. Even if you do write it asynchronous, you might say, what do I do now? That's all what I did. I'm used to getting blocked. What do I do now? So you have to teach the code to do things while it's now being unblocked. It's like you just being awakened and you don't know what to do with your life, right? You're just like in this nirvana state, but you're just like, hey, what is this? What is the meaning of life? That's how the backend process feels in the asynchronous IO mode. So yeah, worker processes. So the idea, just let me just queue this stuff in the IO and let them do the IO for me. And I can do that. So there, I'm trying to emphasize the amount of work that is gone here, right? Because it pains me when I see someone say, well, asynchronous IO is gonna make everything great, and they don't credit the work behind the geniuses working on this stuff. So it pains me. So I try again. This is a tremendous amount of work. Amazing. So beautiful, so good. Okay, so the second IO method to support asynchronous is IO uring, which is a Linux interface to support this asynchronous IO. So the IO uring doesn't exist in Windows, but there is a very similar thing called IOCP, right? Which Postgres doesn't support yet, right? So when we talk about Postgres, the worker method, this is supported everywhere: Mac, Windows, Linux, all platforms that Postgres exists, because it's just a worker, it's just a process, and that's the beauty of the worker, right? And that is the default. Right? So the IO method, the new global user configuration, GUC they call it, is now the default is worker, and you're gonna get the worker by default. So you're async by default, and I think they did it to flush out bugs. Right? So you can switch that to make it IO uring if you have your Linux, a certain kernel version, 5 point whatever, right? And then you can have IO uring. The Postgres use IO uring to do the asynchronous IOs, right? So which is awesome. We talked about that. I talked about how IO uring work. Essentially, it's just a similar idea. There is a submission queue, and there is what is it called? The receive queue, not receive queue, the ready queue, I think. Yeah, so you submit your jobs here, and then you get the results from the other queue. And then it's shared memory between the user space and the kernel space. And that's basically where all the security issues that happened a few years ago with IO ring results from, this shared memory between kernel. It's a sin to share stuff between kernel and user space, right? We always have this kernel mode switch. We switch modes when we switch from user to kernel. That's the only time you can read from kernel space. You cannot read, as a user, you cannot read kernel stuff at all, unless you switch mode. So you can point to the kernel, essentially code stack, and read the kernel code to actually execute kernel stuff, right? But that's IOU ring kind of breaks that rule with the shared memory model. And then, yeah, we found few security bugs, and I think they have been since patched. But yeah, and for a time, I think Google even disabled IOU ring for a while. I don't know if they still does. And I think even in Chromium books, they disabled that because they were worried about security. But essentially, this is the idea of IOU ring. You submit, you get, so you don't have to worry about it. The kernel will do the actual read, and then you get back your result. And then, yeah, you're all happy and unblocked. Same job, same semantic understanding. You're no longer blocked, so you're free. Go explore the world, my friend. But I want to talk about this idea of IOU ring a little bit here. If you think about it, IOU ring itself, the ring itself, is nothing but a file descriptor, just like epols when you do epols, right? So the question is, like, where do you put this file descriptor? Well, one idea is to put it in the file in the backend process itself. So each backend will have a single private IOU ring instance, and that you can issue your reads using that, and you'll not have to worry about anything else. But that problem with that design is you will have a lot of file descriptors, as many as backend processes. And that might be extra cost. Those things aren't free, right? So you increase some memory, you might need to increase the number of file descriptors in your Linux box. In that case, if you ever run out of file descriptors, that's a common error. So you can increase that. I mean, it depends on how much processes your Postgres backend have, right? Yeah, like the default is 100 connections, which means 100 backend processes, but you can increase it. So yeah, so that was one choice. The other choice, they thought, like, okay, let's share them. Let's have a pool of IOU rings and let all the backend share them. Well, that model also is good, but you have now contention. What if two backend processes want to use the same IOU ring? It's like a classic connection pool issue, right? With locking, we have this problem with any connection pool issue, right? Any connection pool implementation. Like, if you don't want two people to use the same connection at the same time, or you don't want two processes to use the same IOU ring, because they may submit the same job and they can overwrite each other work, because you need mutexes to protect them. And they discover that just doing that is more work and more latency than just having a private instance per backend. And I found that discussion in itself so beautiful. I love that design choices. It's like, hey, we explored this and we found that no, the locking from just the contention from sharing these IOU ring, essentially you put them in the parent process, which is the postmaster process, and have every backend process, since every backend process is forked off of the postmaster, it will inherit essentially the file descriptors, right, from the postmaster. So that was the idea, but the contention was just too great for it to work. So they abandoned that idea, says, nah, let's go with a private file descriptor, one IOU ring per backend for that. I just found it very interesting, so I thought I'll talk about that a little bit. So yeah, so that's the state of the art as of 18.0. And the final method set that we have so far is sync, which is classic. We need the old way of doing things. We need to turn this feature off. If it breaks, I need to be able to switch back to the way Postgres 17 used to do, not 16. We can never go back to 16 because we did in 7. I didn't do jack shit, right? I just talk. I'm just an armchair engineer. So what the Postgres maintainers did is beautiful. They architected Postgres 17 is the pinner for this work. Pinner, is that even a word? The pinnacle of this asynchronous IO. So it's a whole architecture different. Right? We talked about the kind of the interfaces they added, right? So we can go back to the way 17 used to do, right? So then you can go back to this approach by switching to the sync method, okay? So then we have 3 methods. Worker, which is the default so far. We have IOU ring, only on Linux. I'm going to put on the screen which version for the kernel. Sorry for the people listening. You're not going to be able to know that. But it's something 5.5 and later. The final one is sync. S-Y-N-K. S-Y-N-C. Okay, so that's the synchronous way of doing things. If you want to go back to the synchronicity, if you're feeling synchronous, right? So what remains? Is this the end of asynchronous IO? No. This is just the beginning. So one of the work they want to do is, first of all what we talked about is reads only. Postgres 18 only supports asynchronous IO for reads. So all the background writers, the checkpointers, the backend stuff that writes, none of that stuff is still sync. And don't quote me on that. Quote Andreas. This is from the talk 2 months ago he did in 2025 August. Okay. Yeah, so writes is not supported for asynchronicity yet. So you can only do reads. I think reads are more important because once you write, you don't really do much, right? You already did the CPU work, right? But I suppose you can do more stuff, CPU stuff, as you're writing, so you can move and do more stuff. But yeah, I think write will definitely benefit. Yeah, so that writes, no writes yet, right? So that work is being worked on in the future. They're gonna start enabling it for all the other, processes that does writes. Yeah, so they're working on enhancing the worker mode essentially to be more flexible. Right? I think today the way they have the worker mode is like the default is 3, and then it doesn't really. You can change it and restart the Postgres instance to pick it up. Right, but it's not flexible. You cannot just change it in runtime. Plus, even if you set it to a large number, let's say 50, it spins up those 50 at the start, and then those 50 will remain there whether they are used or not. So they want to make it like elastic a little bit, so that the Postgres instances, those workers will spin down when they are not needed, and they will spin back up when they are, just to save on memory and just unnecessary overhead, right? So that they're working on that, making the worker better, and the worker for Windows support. So at least for IOU ring for Windows, which is IOCP. So to support IOCP for Windows. Yeah, the final thing is kind of their, what do the Americans say? The fly on the ointment is the saying, I think. Like the thing that keeps rolling all of this is this thing that's called Direct IO. They want it so bad. Direct IO is the ability to skip the page cache and avoid that extra CPU overhead when you copy stuff from page cache to user space. And by doing Direct IO, you go directly to to the disk. Now, there is good thing about this and the bad thing about it. The good thing about it is you avoid the CPU overhead because you read all what you need from disk. The bad thing about it is you're no longer buffered and saved by the kernel, and you don't hit these beautiful caches on the page cache. So every read is slow and every write is slow. I'm gonna say that again. In direct IO, if you open your file with O_direct, then every read goes to disk and every write goes to disk. So every read is slow and every write is slow. You don't get reads that are fast. Right? This only happens when you have a file system and page cache, and you're lucky. Right? And when I say slow, it's like I'm talking like these NAS drives and where you're in a cloud environment and you're going through the network to read. So every read is essentially a currency, and it's expensive to read and write. So direct IO is something they're still working towards, because the Postgres still does this tiny reads and tiny writes all over the place. So you cannot just blindly flip the switch and do, hey, let's do direct IO all over the place. Let's always read from disk, right? And avoid these stuff like why am I doing double caching? I'm already caching my stuff in the shared buffer. Why am I caching again the page cache? That's another benefit of direct IO. You avoid this double cache, so you save in memory, right? With direct IO, but it's harder than you think, right? Every time they turn, and you can turn this developer setting today if you want. On your Postgres, there is a configuration called debug _direct IO. Go try it. Everything will go very atrociously slow. And then Andreas say, don't do it. he just blandly say, don't do it. It's a bad idea.
Able to pull things out of the Linux kernel cache.
It's currently the default will be out of the page cache, and there is an option to use direct IO, but outside of very, very narrow cases, you should not enable that. And it's like the name is debug IO direct.
So don't do it. Don't enable direct IO. But eventually, that's something they're working towards, and I'm very excited towards that work. It's just like the way, there's something refreshing about someone who knows their craft and they talk about it passionately, and that's what Andreas. Go watch that. Listen to that talk. This guy is passionate about what he does, and he even expresses the frustration. He even says, like, sometimes I wanted to just give up on this. Like, I just want to leave all this stuff, because it took him 5 years working on one feature that I talk about in 20 minutes, and then we're gonna close this and you're gonna forget about it. Yeah, that's life, right? But when you do something for the craft, for the love, or for the joy of it, which is, I think that's how I get it, because he just like, he talks about all the details, and I love the details. It's just like the devil is in the details. I love this stuff, It's just, there's something about that. And this is why I do all this stuff, because I never talk about something I'm not interested in at all, right? Now, if you see me talk about a topic, definitely I'm interested in, right? This is just something I do on the side for fun, right? And you guys seem to enjoy it, and I really appreciate you, by the way, guys, for the support. Yeah, guys, that's all for me today. That was the Postgres asynchronous IO. Let's summarize what did we learn today? Not that you guys are here to learn anything, but it's just Postgres. There's this idea of synchronicity, asynchronicity, right? And we move it to the file IO, which is very exciting and interesting and difficult problem to solve. We have all these interfaces that allows you to do asynchronous IO. Postgres slowly started working on bringing them in. the worker idea of having a pool of workers, processes that can offload the IO and have them getting blocked instead of the actual backend process, so that the backend process is free to move and do other things. And we talked about that the just idea of being unblocked doesn't mean you're done. You have to rewrite your code to actually do stuff now that you're unblocked. Remember the nirvana state? We talked about that. No, yeah, just about that. And then we talked about the idea of IOU ring and the challenges there, support for Windows and direct IO, all of that stuff. Guys, I hope you enjoyed this episode. I'm gonna see you in the next one. You guys stay awesome. Bye.